Hi, this video goes with our Chapter 3 in AP Calculus, and the idea that we're looking at today is finding where functions are increasing and decreasing, as well as using that information to find extrema. And so I start out at the beginning. You can follow along in your printed notes. The idea of an interval on which a function is increasing is pretty intuitive. Increasing is just like a car going uphill, like this little car going around the mountain here. If you think of x as something that changes from left to right, as the x's get larger, if the y values get larger at the same time, that means that the function is increasing. So that's what I stated here in mathematical terms. A function is increasing if, as x gets bigger, y gets bigger. We could just write that in here. As x increases, y also increases. That means the function is increasing. A decreasing function is therefore the opposite. That means as the x's increase, the y's are getting smaller. They decrease. Okay, and that's what I wrote in formal notation here. We're always going to use open intervals when identifying where things are increasing, decreasing, or constant. And that is really something that's actually still debated in mathematical circles a little bit. I would say that we should say that the function that I just doodled here would be increasing all through here, but then at this point, it's a little unclear exactly what's going on in terms of increasing or decreasing, because over here, the function is decreasing. And up till that point, it's increasing. And I would say at the place where it switches, it is neither increasing nor decreasing. And so that is why we would use open intervals. To continue on in your notes, you see that we're going to use the first derivative to test where functions are increasing, decreasing, or constant. And that very much goes with the sort of doodle graph that I just had on the previous screen. We'll draw a new one just for the heck of it, okay? So if we had some function that went like this, it went uphill and downhill and uphill, and then let's say it plateaus. Okay, it's a really crazy function, okay? Say we have something like this. All through here, all of your little tangent lines would have a positive slope. And so if you look at the first kind of bullet point up above, if our derivative is positive, meaning we have positive sloping tangent lines, then we say that the original function is increasing. Now watch your nomenclature here, okay? This is saying the derivative is positive, and that means the function is increasing. Don't mix those up too much. Sometimes people will say, well, because the derivative is increasing, the function is positive, and that's backwards, okay? So be careful that you're saying the word positive where you mean positive and increasing where you mean increasing. Then you notice over here, we have some negative sloping tangent lines, okay, on that part of the function, for example. So the second bullet says if your derivative is negative, that means that the function is decreasing. Great. And then we have things that are called critical numbers, okay? So a critical number could be where the derivative is 0. It can also be where the derivative is undefined. But right here, I'm just talking about 0. Where the derivative is 0, for that particular moment, we have a function that is not changing. At that exact instant, there's not change. And so this is a critical number. This is also a critical number. And then over here, in this whole section right in here, we have a derivative that's equal to 0, and so that function is constant in that interval, okay? These two spots here are critical numbers. It's where the function changes from increasing to decreasing or from decreasing to increasing, okay? And those end up being extrema, as you can see in the picture, okay? So the first derivative does tell us some things about the shape of the function in terms of uphill versus downhill versus flattening out. So this is a formal definition of the words critical numbers. We saw this a few days back as well. In between where the function is negative, or the derivative is negative and where the derivative is positive, there has to be a moment where the derivative becomes 0 or undefined. And those values, as we have discussed in the past, are places that we call critical numbers. All right, so here is a block of 4 questions that we're going to use, 4 examples, to teach the idea of looking at increasing and decreasing intervals. The steps will always be roughly this. First, we'll take the derivative, the first derivative. We will set the derivative equal to 0 and solve for x. We also will think about where the derivative is undefined. So as we talked about in our previous lesson, those two things together, where the derivative is 0 and where the derivative is undefined, those two things together are called critical numbers. Okay, so those critical numbers are going to break the domain of our function into intervals. We then will do some interval testing. We will look for the sign, positive or negative, of the derivative in each interval. And we'll do that by picking some number from inside of each interval, not the endpoints, but from within the intervals. The sign of the derivative is going to tell you if the original function is either increasing or decreasing. So if the first derivative is positive, that's going to mean that the original function is increasing or going uphill. If the first derivative is negative, that's going to tell us that the original function is decreasing. Okay, this is something that might be helpful to write at the top, say, of your homework paper, just so you can keep referring back to it, because that's the big idea. Okay? Let's take a look at an example that we can do together right now. So this one says find the open intervals on which that function, the quantity x minus 3 to the 2/3, is increasing / decreasing. Okay, so the first derivative can be found by thinking of chain rule. Bring the 2/3 in front, keep what's in the parentheses, reduce the exponent by 1, and then the derivative of the inside in this case is just a 1. If I write this in maybe more friendly notation for myself, I've got a 2 upstairs, a 3 on the bottom, and a cube root of the quantity x minus 3. Now, I need to find the critical numbers next. Now, critical numbers are where the derivative equals 0. So I want to think about that. So imagine I have a 0 over here. What do you think? I think if I write this as 0 over 1, I end up getting the statement 0 equals 2, and that does not happen. So there's no solutions from that. Okay? I also would like to think about where the derivative is undefined. So I need to think about, going back for a second, I need to think about this expression and think about it being undefined in terms of finding the other critical numbers. So what do we think about that? I think I'm going to get something undefined if I'm dividing by 0. And dividing by 0 is going to be caused by x being equal to 3. So f prime of x is undefined if x equals 3. So out of those two cases, the derivative being 0 and the derivative being undefined, I only have one critical number, which is 3. The domain of my original function is all real numbers. So starting from negative infinity and going up to 3 will be one of my intervals. The other interval will be the remainder of the real numbers, 3 on up. Okay, I'm not including 3 itself. Notice I've made this chart. I think this chart is a nice organizer for this point in time, this part of the year. We're going to take a test value from each interval. So I'm going to choose, let's say 0 and maybe 4. Okay? And I'm just picking random numbers. 0 is in between negative infinity and 3. 4 is between 3 and positive infinity. You can pick anything in the interval. Now notice in the next part of the chart, all I need is the sign of the derivative. I don't need the value. This will save you time. You don't need to get your calculator out. You just need to think. So I'm going to imagine now putting 0 into the derivative. So in my mind's eye, I wouldn't actually be writing this except I'm trying to explain it. In my mind's eye, this is what I'm seeing. Okay, now is the result of that going to be a positive number or a negative number? Hopefully you know that that will be negative, so I'll write negative right here. Okay, and if you didn't know that, maybe you do need to use your calculator, but I hope you don't. Okay, now I'll also test the sign when I plug in 4. I'm plugging into the derivative. Notice that. I'm looking for if the tangent line is sloping up or sloping down. That is a slope question. So I need to plug into the derivative. When I plug in 4, the sign of my derivative is going to be positive. Positive sloping tangent lines means that the function itself, the original function, f. So my conclusions about the original function would be that my original function is increasing on 3 to infinity. And because the derivative here is negative, that means my original function was decreasing until it got up to the value of 3. Okay? Please listen to any part of that again if it was unclear to you, and if you're okay, let's go on to example number 2. Example 2 has the same exact directions. Find where the function is increasing or decreasing. This derivative requires remembering some quotient rule. So I'll start out with the denominator times the derivative of the top minus the top times the derivative of the bottom. And this is all over the denominator squared. Okay, when I clean this up a little smidge, I get 2x squared plus 32 over 16 minus x squared quantity squared. Okay, so understand that this is in fact the derivative. To know what my test intervals are for my chart, I need to find the critical numbers. So I need to think about where the derivative is 0. So imagine that this fraction is set equal to 0, which means the top has to equal 0. So I'd have 2x squared plus 32 equals 0. This is not going to give me any solutions in the real number system. Okay, it gives me some complex solutions, but that's not part of drawing a graph in the real number system. So now I'm moving on to where the derivative might be undefined. Now this will be undefined if the denominator equals 0. So I'm going to write 16 minus x squared quantity squared has to equal 0, which is equivalent to having the inside parentheses equal 0, and I factor that. It's a difference of squares. And hopefully you can see that my critical numbers are actually at -4 and +4. So my intervals are as follows: negative infinity to -4, between -4 and +4, and 4 on up. Notice I do write my intervals from smallest to largest. I'm imagining the number line as I write those. I'm going to pick a value from each interval. Okay, so I just picked some numbers from each one. I do like picking 0 because I think it's easy to calculate. And understand here, I want to figure out the sign of my derivative so I can write a conclusion about my original function. Okay, all of those numbers that I wrote in green are going to be substituted into this derivative. Okay, and I'm not going to worry about the actual number. I just need to know positive versus negative. That's what sign means. So if I put -5 into this function, the top is certainly going to be positive because of squaring, making something non-negative. And the bottom is going to have the same thing happen. So I will have a positive result. If I put in 0, I'm going to get 32 on the top. I'm going to get 16 squared on the bottom, and that's going to be positive. And if I put in 10, still have something positive. So all of these return a positive. So what does that mean? Well, I know because of that rule that a positive derivative means the function is increasing. Can you envision how this would be increasing all the time? Look back at the original function. What's happening at those critical values of -4 and +4? I hope you recognize that those are going to be vertical asymptotes. The function itself is not defined at 4 or at -4. So there are these asymptotes, and the function actually ends up looking something like this. There's a part that's increasing over here. There's a part that's increasing right in here. And then there's another part that's increasing here. Okay? All of those sections, if you're driving on the graph, like say you're driving your car. Here's your car. Wow, it looks really good. Okay. So if you're driving your car from left to right, overall, you'd be going uphill, and then uphill, and then uphill with your car. If you're going uphill with your car from left to right, that means the function is increasing. So that's what's going on with example 2. Let's look at example 3. Oh, just kidding. I forgot I put this in here. Okay, so maxes and mins we have talked about on intervals. When we talked about the extreme value theorem that day, we talked about how extrema occur at critical numbers or at endpoints. We also can think about critical numbers as being where the function changes from negative to positive or positive to negative. So for instance, if we had something that looked like this part is increasing, this part is decreasing. Right here, the function changes from increasing to decreasing. Or in other words, the derivative changes from positive to negative. If the derivative changes from positive to negative, that means we have a maximum. Okay, that's what I just drew right there. If we have the reverse of that, say we have a graph where we have decreasing and then increasing later. Okay, this part is decreasing, this part is increasing. There's a spot here where it changes from one to the other. This is the example where the derivative is negative first. See how this part would be tangent lines with negative slopes? And then positive after that. So tangent lines with positive slopes. At this point, we would have a relative min. Okay, so notice that on my screen, the colors match, right? The blue picture goes with the ones I wrote in blue. The red goes with the red. Now, if you have something without a sign change, like we did in that example we were just talking about, wherever it went, here. There wasn't a sign change, right? We stayed positive all the time. Did you see a hill or a valley here? You did not, okay? So if we do not have a sign change, no sign change means no max and no min. Excuse me. We have to have a sign change. This process of testing intervals to find maximums and minimums is what is called the first derivative test. We actually have been doing the first derivative test without really pointing it out. This process with the chart and looking for sign changes, this process here, is the first derivative test. All we need to add to this is saying, well, if it goes from being a negative derivative to a positive sign for the derivative, that means we're going downhill then uphill. That means right here at 3, at x equals 3, we have a negative to positive means a min. That's first derivative test. Finds extrema, okay? So I wrote out steps here. I don't know that I will read all these to you. I don't know that that's a good use of video time, but please do read that. It does summarize everything about finding extrema, and understand that the first derivative test can be used on all functions, not just closed intervals. It's not the candidates test. The candidates test is what you want to use if you're just looking at a closed interval. This works for everything, okay, when you don't even have endpoints. I think what I'll do is just have you guys pause the video now that we've talked a little bit and have you try 3 and 4, okay? So try the problems with the video paused. And in just a few seconds within the video, I'm going to show all the answers on this, but I just don't want this running too long time-wise. So go ahead, pause the video, and then come back and check your 3 and 4. Okay, welcome back. Hopefully you have something like this written on your page now. Find the relative extrema. If we don't have a closed interval to do candidates testing, means that we have to do the first derivative test, this chart kind of thing we're talking about, okay? We find the first derivative. We find critical numbers. The only critical numbers I found were from the derivative being 0, which was -1 and +1. Those values determine these intervals. And then I can pick any points from within the interval. You can see there which ones I picked. Regardless of what you picked, your signs should end up being these, positive, negative, positive. And so what that implies is if I were to try to think about what the graph would look like without working on it very hard at all, I would just say, well, if this is my number line, my x-axis, I know that at -1 is the value in between those intervals. The function changes from going uphill to downhill. and then at 1 it's going to change again. So here's 1, here's my 0, okay? So I have some sort of function that's going uphill, downhill, uphill. I don't really know where this is placed on the graph relative, istically. I don't know where the y's are, so I haven't bothered to do that, but it's something that's going uphill, that's this, then downhill, that's this, and then uphill again, so that's this. So it's something like that, okay? I don't know exactly, but something along those lines. When my derivative changes from positive to negative, or the function changes from increasing to decreasing, I have a max. So there's a maximum at x equals -1. And then here where it changes from the derivative changes from negative to positive, that means the function changes from going downhill to going uphill. So here at this location, right here at 1, there is a min. Okay, and that answers the question. The question was to find the extrema, and my extrema are at -1 and 1. If I needed ordered pairs, I would plug back into my original function, okay, to get the y coordinate. In this one, this is what your chart should look like. You have your derivative, you factor a little to help yourself find the critical numbers, which are just 0 and 3. This derivative is defined for all real numbers, so there's no values from the other part of the critical number definition. Here, the fact that 0 is a critical number, if I look down here and I say, well, is there a sign change? There's not. It's just negative, negative. So no sign change there, so no max or min. However, if I look next door, this changed from a negative to a positive value for my derivative. So at 3, there is a sign change. So I would write about that by saying at x equals 3, the derivative changed from negative to positive. So I'm changing from going downhill to going uphill. That is a min. So at x equals 3, there's a relative min. Okay, and then I can tell that there's something interesting that must happen at 0, but it's not a min or a max. And my guess is that because we have decreasing, decreasing, I think it might be something like going downhill, and then it looks like it's going to turn, but it doesn't. It just decreases more, and then comes back up. So my guess is that this kind of point right here is what we have when x equals 0, so 0 comma whatever. And this point down here is the min that we referred to a second ago. And again, if I needed these y coordinates, I'd go back to the original function and plug in my x's to find the y's, okay? That's all you need to know in order to be very successful on this lesson. And thank you very much for watching a sort of long video. Tomorrow or the next day at school, please bring your math book. Actually, for the next couple of days, bring your math book. We'll be working in class on this lesson for a couple of days. Thank you so much. Have a great night.